Okay. Let's get started then. So, more kinetics. Always, never ending. We will do our Excel stuff today. I have that ready, but let's take a moment to do some terminology that I should have done yesterday, but I didn't. So with regard to mechanisms of our reaction, I think we had our absolute favorite reaction of all time. The same one as always. We saw that this was the overall reaction. And we had come up with certain, steps that could be done to make this reaction happen. And I think the one that we had put, did we do? Yeah, we did oxygen gas. So we had something like this as one step. And then we had a second step, which was turning into carbon dioxide, right? And that was step 2. And we saw that this one was slow and this one was fast. These are what are called elementary steps. And so these are just kind of the, each like individual step in the reaction as it's happening, just step by step. Whereas overall, you may have a whole bunch of different steps happening. If we look at just one step at a time, that's called an elementary step or an elementary reaction. And we're going to see that elementary steps they can be one of 3 things. They can be unimolecular, bimolecular, or termolecular. And so, for example, a unimolecular steps rate law would just be first order, right? If we were to just look at the stoichiometry of it. A bimolecular reaction could be something like this. Either we're using 2 of the same molecule or we're using 2 different molecules. Bimolecular ones would have 2 components reacting. And then for termolecular ones, we could have same thing. Or we could have 3 different molecules, or we could, whatever, doesn't matter. 3 kind of components there. These ones, unimolecular and bimolecular steps are pretty common. However, not rate, rare. Termolecular steps are not so common. Because if we go back to way back when we talked about how reactions are happening, if we think about the fact that molecules need to collide in order to react with each other, if we think about the probabilities of 2 molecules hitting each other with the correct energy and orientation, it's pretty low. And so now if you want to think about a third molecule coming in at the same time with the right energy, with the right orientation, just the odds become so low of it really happening that it's kind of, I don't want to say impossible, but highly, highly improbable. So we very often do not see termomolecular reactions in elementary steps. They're not so common, and so we're going to see that often we would probably try and come up with mechanisms that avoid termomolecular reactions. Sometimes we can't. Sometimes they're there, and that's the way it is. But often that's not something we like to see. So, hooray! Cool. So there's our kind of terminology here. So, for example, we're looking at this elementary step here. The first one would be bimolecular, right? But lo and behold, we've put our second one as a termomolecular reaction, which possibly means that this would not be a very good mechanism. And in fact, we could think of a different one, perhaps, that would not include a termomolecular step. But let's not worry about that right now. So with that in mind, there's your terminology for us. So we're going to talk about reaction mechanisms. Yeah, let's do this problem, and then we'll talk about. No. I want to do the Excel stuff first. All right, hold up. Let me pull up Excel. We're going to do 2 problems on that, and then we'll come back to do more reaction mechanisms. Okay, so I have an Excel spreadsheet here where I have my my data that's put in. In this particular one, we're looking at chlorine monoxide breaking apart into chlorine and oxygen. And so here's some data that was collected. We have the time in milliseconds, and we have our molarity. So if we wanted to solve this problem by finding its order, rate law, and rate constant, we can do that from the data that we're given. So this is kind of going back to yesterday, working with different types of reactions. So, good night. How we would do this, once you put in your data, you're going to want to take a look at the natural log of the concentration as well as the inverse. How we can tell Excel to do this is just have it calculate the natural log by inputting a formula. So ln of B2, so it'll be the natural log of my concentration. And I can just drag this down, and it's going to do the same thing for all my concentrations. For this one, I can do the same. We'll do equals 1 over B1, because that had my data. Not B1, B2, I'm sorry. And drag that down. And so now we have calculated the natural log for all those as well as the inverse of them. So we kind of have 3 options for the order of the reaction, right? It could be 0 order, 1st order, or 2nd order. And how we're going to look at that is we're going to be graphing these. So in order to do that, you'll go to Insert, Charts. Whoops. I meant to, why is this? Oh, there we go. We want a scatter plot here. I don't know why it's not showing that, but that's an option I have. So you'll click this button here, and it should pop up. It'll be the top left option that you have there. That's not showing for me. If we look at this graph, does it look linear? I hope that's not what anyone would consider linear. So that is not. It's not going to be 0 order. Remember, if it's just a flat line right this, it would be 0 order, but this is not. So it's not linear. Goodbye. It's gone. Let's try looking at the natural log comparison. So again, I'm going to go to Insert, Charts, Scatter Plot. Is that linear? Not quite, right? We're seeing this kind of slopey thing. So that's probably not the right one either. So let's now compare our last one. Put our scatter plot here. Aha! This looks pretty linear. Right? Things are a nice little line here. Yeah, exactly. So this is definitely linear. So always check all three, and you should get something that makes sense, right? You shouldn't have to like say, that's kind of linear. Like all your homework problems and all that, it will be very obvious to you. So with that, now what we can do, so we found that this is now going to be a second order reaction, right? Because we can see that the inverse graph is going to be the one that is linear. What we do, if we go ahead and right click this, we can add a trend line to it. We can see again very clear that this is a linear trend line. I'm not sure why this is not showing up when I'm screen capping, but whatever. Just right click one of the dots and you'll have the option to add trend line. What you want to do is display the equation on the chart. That'll give you the equation for your line. So remembering, here let me put this aside for just a second. Remembering for a second order reaction, we have 1 over the concentration equals KT plus 1 over the initial concentration, right? Notice that KT is our MX component of this reaction. And so if T is our X, that means our slope is going to be the rate constant. So if you really wanted, you could do rise over run, figure out the slope that way, but handy dandy, Excel has already given to us the equation in slope intercept form. So we can see that K is going to be equal to 7 times 10 to the 6th power. So makes things a lot easier when Excel will calculate it for us. There's no reason to say, okay, I'm going to take the X value of 0 and the X value of 30, and then I'm going to take these two Y values and subtract them and get the rise over run to make our slope. Just have Excel do it. It's a lot easier. And so for this particular problem, we're going to see that K is equal to 7 times 10 to the 6th for our rate constant. If we saw that this was a second order reaction, that tells us that that would be our rate law. I guess I should actually give you the reaction, huh? Here's our reaction. Our rate law is CLO squared. We know that because it's second order. And now that we know the K, we can do all our fun sorts of things with it. But what else? What was I going to try and say? I guess all we had to do was find the K, so our problem is done. Hooray. We did it using the magic of Excel. Hooray. All right, here's another one. All right, another reaction for us where we are asked to find the concentration at 10 minutes. I guess I should pop open Excel. Aha. Okay, I'm done with this graph. It goes bye-bye. If you are doing this on your homework, you're using Excel, I would just write used Excel and then maybe write your equation or something that you got out of Excel, just like as your work. Alright, so here's another one. Let's see what the concentration is going to be at 10 minutes for this. I have our time and our concentration data that we gathered from our lab experiment. Doing the same thing, we're going to do, this is going to be equal to the natural log of B13, I guess, in this case. And stretch that down. And let's go ahead and do this one too. It was 1 over B13. Okay, we now have all the numbers we need. let's go ahead and compare them. So we'll go insert charts. We'll choose our scatter plot. That's interesting. Is that kind of linear? Let's see. We can add a trend line. Let's see. It's kind of sloppily linear. Maybe. Let's go ahead and look at the other two just to see if we get better results by comparing them. Let's go ahead and compare our natural log graph. Oh, this looks pretty linear too. Let's have a look. And it actually looks like all of our things are indeed along a line, whereas in this one we had kind of residuals up and down. We can see there's a slight curve to it. And in fact, a different trend line would probably be better for this one. We would probably say maybe this is an exponential trend line instead. And lo and behold, the exponential one fits a little better. I can't get rid of the other one. Well, whatever. So this one definitely looks a little bit more linear. But let's just double check again. Let's make sure that our inverse one is not the correct answer. In this case, yes, it looks indeed that we do not have something nearly as linear as the other one. So, I would say that this reaction is going to be first order because the natural log graph is the one that is linear. Once we have that, with our trend line here, I don't know why I can't ever like click the points. There it is. Let's go ahead and put our equation out. And this equation is going to tell us how to solve this problem, right? So I'm asking what's the concentration at 10 minutes. 10 minutes is going to be a time value, yes? So if we pop back to this, remember that's an x value. So we have our equation. Excel has already given to us that y equals negative 0.0008x plus, or no, minus 0.6931. So if we are going to plug in our x, we can do that. However, note that our data, our graph is given in seconds, not minutes. So we're going to need to adjust this to 600 seconds instead. Just keep that in mind. So if we do this, we can go ahead and plug in 600. We can solve that equation graphically. 0.0008 times 600 minus 0.6931. Wait a second, something's gone wrong here. How did I get a negative number? Oh, because that's negative KT. Yeah. My mistake. We have it negative speaking. We should make that a positive. Remember that this is negative KT. We're going to probably want to make this positive in this case so that things make sense for us. Remember that we do this too because it's a decrease in concentration. So we can't, of course, end up with a negative value here. So let's make that positive instead. Is that going to help anything? It tells us that we've used up 0.2131. If we go back to our Excel sheet, we can actually kind of... Oh, wait, you know what? That's the problem. This is natural log. We have to do our stupid thing again. I'm sorry. I keep forgetting that the... this is our formula for first order, right? So we're actually getting that the natural log of the concentration is going to be negative 1.17 or whatever. So we're going to have to do the concentration will be equal to e to that. Remember, since this is a natural log graph, if we were to go back to base units, we have to do e to that. So, my bad, we're good. E to the 1.17, negative 1.17, I guess I should put. We do that, aha, we have a reasonable answer now. On our units, there would be a molarity. Right, and so let's just double check to see if this answer makes sense. Popping back to Excel. We're seeing, okay, at 500 seconds, we're at 0.33. At 1,000 seconds, we're 0.21. If we're looking for 600 seconds, we're going to be in between those values. So we would expect our molarity to be in between those two, right? And so therefore 0.31 makes perfect sense. It's, you know, a happy kind of it works. Suffice it to say. So our number is valid here. So we're going to go ahead and indicate that we are indeed happy with our value of the concentration at 10 minutes into this reaction. So basically, you just need to kind of remember those three equations that you have for your integrated rate laws and how to apply them. Don't forget natural log is there, as well as the inverse. So if this were second order, we would make sure to use the inverse formula instead, right? So, cool. Any questions on that one? Or the one we did before. I'm going to just pop open the Excel again just so you can see like all the important bits. So in this, we've discussed how to calculate these values very quickly, as well as kind of how to graph these, and then how to apply the information that we get out of them. Coolio. Any questions on those? Alrighty, then back to chemistry. Alrighty. Back to mechanisms. So, yesterday we talked about a particular reaction that had a slow first step and a fast second step, and we were able to see that the rate law from the rate determining step is what we found experimentally, and we were able to kind of prove or disprove some mechanisms. Not really prove, but we were able to disprove a different one. Let's see a case where we have a slow second step. So I have the reaction here. It's all our favorite elements. It's again nitrogen and oxygen. And this is turning into 2 nitrogen. Yeah. Okay. Alrighty. Experimentally, the rate law is going to be, I believe, this guy, yes? Yeah. However, we know that termolecular stuff is not likely. So it's probably not just happening in the one step that is written like this. So some scientists have come together and have proposed the following other steps. Step 1 is proposed as being NO plus O2 turns into NO3. And then step 2 would be NO3 plus NO turning into our product. Notice we would have the intermediate of NO3 in this case. But look, we have entirely bimolecular reactions. So that's already a good thing, right? And it's proposed that, or rather, we have to kind of work with this. So if we were to just look at the rate laws for these particularly given reactions, we could say that rate is K NO times O2. Or if it's the second step, it would be NO3 times NO. Do either of these agree with our rate law directly? Not quite, right? We don't have an explicit NO2 squared O2 thing going on here. But here's where the fun begins. If we suggest that step 2 is the rate determining step, we can assume the first step, which is nitrogen monoxide plus oxygen, is fast and now reversible. Because things are not happening right away, often your intermediates, remember, are higher energy species than your reactants. Which would therefore change our reaction slightly. We now will put a double arrow instead. So if we suggest that the second step is the slow step, that means our first step would be happening, but it's probably also breaking down. Because if it were the case where our intermediate were nicely stable, we would then probably be okay to just start reacting as more of it builds up. And so that would actually make our first step slow. But if our second step is slow, we probably have a reversible first step. That's gonna here. Let's put it here. If our second step is the slow one, that says to us that, hey, if our NO3 here, which is our intermediate, is just chilling there, it has enough activation energy to go right back down again. And so it'll probably do that. If we compare with something where we had a slow first step, we saw that we, maybe we're going like this or something. If we're looking at our NO3, it's more likely to just keep on going, right? Just in terms of the energy humps that it has to go over. So we're going to see that if your second step is slow, your first step is probably going to be fast and reversible. And so what that means, that the rate of our forward reaction is probably going to be the same as the rate of the reverse reaction. Or suffice it to say that we have two potential ways we could describe this rate. We could also say it's equal to the reverse reaction, the disappearance of the product, right? We could say the disappearance of the reactants or of the products. So, looking at these, if we're going to say that the rate is the same because they're reversible, it's happening back and forth, we can say, therefore, that these guys are going to be equal to each other. And This is always it's always interesting to teach this because it's kind of like why are we doing this? If we look at our rates here, our rate laws, if we're going to suggest that the second step is slow, we're going to see, is there a way that we can get these two to kind of work with each other? We can't really have NO3 as part of our rate law because it's an intermediate, right? But I'm just going to copy those rate laws. Let's not. If we solve for NO3, our intermediate concentration, not K2, I'm sorry, the reverse rate constant, we can do that, just mathematically, right? If we saw that the rate for this entire step was NO3 times NO, if we plug this stuff in, if I substitute NO3, oh, look where we're headed with this. I'm just going to go ahead and call this crap K. It doesn't really matter. We don't really have a value for K at this time, so I'm going to just lump all this K times K1 over K to the K minus 1. Whatever, let's just call that all K. We do that, and we can end up getting our experimental rate law out of this stuff. So, by doing so, by substituting in components from our first rate law into our second rate law, as exciting as it is kind of the holy WTF moment that this is, we can make it work. So notice that again, this is our experimental rate law. We have some constant times NO2 squared times O2. And we were able to get that even though neither of our steps had that explicitly. We were able to kind of do some substitution to make it all work out. So with the slow step, second, we can use the first step to kind of assist in determining if a mechanism is possible. So again, this showing that we did get the rate law out for this particular mechanism is evidence that supports it. It does not, of course, prove that this is the mechanism. It's just evidence that is supporting that. So it could be a potential mechanism. So remember, this is kind of an easier way to either cancel out a potential idea or to support one. So in this case, we're supporting one. Let's see if I have another example here. So we can do it again. Yeah. Okay. I do have another example, so we can see this. So, what is our overall reaction? 2 N2O5 turns into 4 nitrogen dioxide plus 1 oxygen. And it turns out that the rate is given as such, unimolecular rate. All right, and here are there are going to be 3 steps now that are proposed. I'll put a little bit of space here. First step would be where we're suggesting this one is fast and reversible. The second one is, oh gosh, we're breaking this down to N2O3 plus 2 nitrogen dioxide plus an oxygen. And then the last one is N2O3 plus oxygen. I'm sorry, it's ozone, not oxygen. I can't read. 2 nitrogen dioxides plus our oxygen. Okay, there we go. It's always fun to copy these, right? So, this is the kind of proposed step, or rather steps, that could lead to this overall reaction. So, because we know that the rate law is not the same as just the two molecules, it's only dependent on one of them, this is not suggesting that the overall reaction is one step. So we probably have multiple steps going on here. So, with this, if we were to look at our slow step, our slow step says that the rate is equal to N4010 for our slow step. So let's see if there's a way we can mess with our fast and reversible one to try and make this happen here so that we can get this equal to our experimental rate law. So, does this equal? That's our kind of task here. And that'll let us know if this is a potential mechanism or not. So if we look at our fast reversible step, we're going to have N2O5 squared. Remember, for elementary steps, our rate law is dependent on the stoichiometry. And we're going to say that this is going to be the same as the reverse of the opposite reaction. That they're happening at the same time at the same rate. They're in equilibrium going back and forth. All right, if we go ahead and substitute in our N4010, or if we solve for that rather, we get this, right? Just moving the K. I keep writing K2, it should be K-1, opposite reaction. If we look at that, we can say, okay, well, let's see if N4010, let's see what that would equal. So that's going to be K times K1 over K-1 times N2O5 squared, which again, we're going to just break. That's the ugliest brackets I've ever seen. There we go. Just some new K times N2O5 squared. Is that the same thing as this? No, it is not. So by manipulating our original equation, we see that we get something that does not agree with the experimental rate law. And as a result, we can say that this is not an acceptable mechanism for this reaction. So this tells us that this mechanism is invalid. So remember, only two things you can do with these. You can say, yes, it supports it, or no, it does not, and therefore it's invalid. So because we saw that messing with these steps did not end up giving us the rate law that we're looking for, that we determined experimentally, that this dimerization is not a good first step before our slow step. So that's not what's happening here. So as a result, this mechanism as proposed is not valid according to the kinetics data. So that would be an example where you will get one that doesn't work. Okay? So process is the same here. We're just messing with our reversible reaction, looking at its forward and reverse reactions and trying to kind of conglomerate those to see if we can get it to fit the kinetics data. And so, again, because they did not agree, we have an invalid mechanism. Hooray! How exciting. So we would have to propose something new if we really wanted to make this work. So, hooray. Any questions on that one? Okay, well then let's talk about our last kind of bit of kinetics here. If you guys want, tomorrow we can go over kinetics some more, or we can start equilibrium. It doesn't really matter to me. Equilibrium is a shorter chapter than this one, of course. So we'll try and get through as much as we can, of course. A catalyst is something that speeds up a reaction and is not consumed in the process. We're going to see that... actually, I think there's a nice example in here somewhere. Yeah. Okay. Okay, so let's talk about chlorine atoms. If we have a chlorine atom, this reaction can happen. And what we can do with that ClO then is break that with another ozone. And we can look at the kind of components here. If we look at overall what's happening, notice that in our overall reaction, this chlorine doesn't even show up. It's going to be a catalyst, and we can say that because it is first consumed, but then produced again. So catalysts are going to be kind of, they're used and then regenerated. So we've used our chlorine atom, and then we get it back out again at the end. An intermediate, on the other hand, is going to be produced and then consumed. So it's kind of the opposite idea here. So a catalyst is going to be used and then regenerated, whereas an intermediate is produced and then it's used up. So neither of them will show up in your overall reaction. Neither intermediates nor catalysts show up in your overall reaction, but they are there in certain steps, and they kind of function in different ways. So this is one why how the ozone layer gets depleted if you have a chlorine radical in the atmosphere. Chlorine radicals can come from CFCs, chlorofluorocarbons, which are bad things that were banned in like the 80s or something because they destroyed the ozone layer because of this catalytic process. As you can see, we keep making our chlorine, so it can just keep doing this reaction with the ozone over and over and over again. And so it's just there to mess things up. And so catalysts, they work by lowering the activation energy through one of two ways. They will first offer a different mechanism. So while one mechanism may have a certain amount of activation energy, if you add a catalyst, you might have it undergo a different mechanism. And that different mechanism would have its own activation energies. And then a second component would be it can aid the orientation of molecules. So it can just help them to collide properly. And so step 2 is going to be more kind of the biological stuff that we're going to see. Enzymes are going to be very important catalysts that are there to make sure that molecules react in the proper orientation and kind of force them to collide properly in order to react more quickly. So generically speaking, here's some general reaction. Here it is. Again, we have our time or reaction progress. And then we have our energy. Maybe if we throw in our catalyst, we'll end up lowering our activation energy. So maybe instead of, in this particular one, we have a one-step reaction. We'll say it has EA1 or something. Maybe our catalyst can give us an alternate two-step mechanism, which has, in this case, it would have a lower activation energy. And so with the catalyst, we're going to end up lowering our overall reaction energy. In this case, it doesn't have to add more steps. It could make it still somehow one step. Or it can make it 3 steps. Like, it just is a different mechanism to get the same kind of outcome. So just throwing the catalyst in there is just going to change your mechanism. It's going to either make things easier to collide or change that mechanism. So in either case, you're lowering your activation energy. Lowering your activation energy means faster reaction. Remember that we had our kind of general Arrhenius equation here. If we lower the EA, we're going to basically decrease the natural log of K, but that's going to increase our K overall. Because natural log is kind of the opposite, right? It changes exponential into the other way. So that's a good thing. This also tells us that we could have the same rate at a lower temperature instead. So maybe we need a certain temperature for a reaction to happen, but throwing in a catalyst would make it happen at room temperature or at 37 degrees Celsius. That's going to be more important for biology. So we remember perhaps that we can double the rate of a reaction by increasing its temperature by 10 degrees Celsius. Remember, in our bodies, we are stuck at 37, right? We don't change our temperature. And so we basically have proteins to make new mechanisms for reactions that will allow them to happen at whatever rate we want at that given temperature. So, it's a very important process because, as we know, fevers can kill us. It's not so common nowadays, but back in, dark times and stuff, if you got a fever, you would die. Just because changing your body's temperature would change the rates of all these different reactions happening, and doing so would throw everything into chaos, and then there you go, you die. Our bodies are quite sensitive, as you may know. So we're going to see that catalysis is going to be a super, super important area for biology. You have enzyme kinetics, you have classes just on enzyme kinetics, and the study of enzymes is continuously ongoing forever and ever, including drugs and all that sort of good stuff. So anyways, that's the whole point of catalysts. So they're going to provide a new route for you to do your reaction that's going to have lower activation energy. Hooray. Important to note again, they are not consumed by the reaction, they're produced again. What do I want to go with this? That's all I want to talk about catalysts, honestly. They will not be consumed in your reaction, and they speed things up. That's what I want you to know. And also how they speed them up. So the two different kind of ways there. Our last kind of bit here for kinetics is going to be half-life. This is something we'll talk about more in nuclear chemistry, but we'll talk about it here a little bit. Half-life is the amount of time which is often abbreviated T1/2, required to, or rather for half of the original amount of whatever to be consumed. So it's the point where, if you start with 15 molar of whatever, it's the time for you to reach 7.5. Very often, half-life will follow first-order kinetics. Although you technically can have half-lives that work in terms of zero or second-order kinetics. So we kind of have options here. Whoops, I've just destroyed that. With regard to half-life, if we take our first order kinetics, we have our negative KT plus ln AO. If we want to look at what the half-life would be, we're going to say that if we're going to put these together, remember that, oh my gosh, I need parentheses. If we subtract our logarithms, they're the same thing as dividing them. Isn't that exciting? It's negative KT. If we have half the amount remaining, we're going to say that we have ln of half if that's 1/2 over 1 then. That would be equal to negative k times the half-life. Solving this, we can say that T1/2 is going to be equal to negative ln of 1/2 over k, which is going to equal negative 693. I need to double check this on Google. ln of 1/2. ln 0.5. Yeah, 0.693. Divided by k. So we can work with this sort of thing. So it's just a way of relating kind of important points on a graph. So if you're plotting your just time and concentration, that looks for a first order reaction, that's exponential decay. We're looking at the amount of time it takes for that to kind of be halved. It's just kind of an important thing that we'll talk about more in when we get to nuclear chemistry. But for right now, it's just going to be an exciting time. So if we start at, I don't know, 10, this amount of time is your half-life. And it turns out that if you're following first order kinetics, the amount of time it takes for you to go to 5 to 2.5 would also be your half-life. Your half-life would be a constant as a result of this. So it's just the time for you to deplete your concentration by half. And if you were to then go to 1.25, you would say, okay, that's another half-life that's happening here. So we can relate the half-life to the rate constant using this relationship, using the natural log of 1/2. There are technically half-lives that you can make with other orders of reactions, but they really are not very common. I mean, we're not really going to use those. So for us, half-life is going to be purely a first-order process and not a zero-order or a second-order. So, hooray. But, I mean, technically we could derive them if we really wanted. Does anybody really care? I mean, we could say, forget it. We can derive it from the second-order or first-order zero-order integrated rate laws. But I'm really done with kinetics. I don't want to ever talk about kinetics again. Though I guess I'll have to, right, when we do our review session. But we are done with kinetics. Happy face. Very big happy face. We have made it. So, tomorrow we will start equilibrium. Unless you guys have more questions about kinetics, I'm happy to go over those. We have time. No, kinetics are not fun. Well, maybe they are. I just, I don't know, it's too much just general math and stuff for my taste. Not that equilibrium will be any better, but hooray. So, with that, tomorrow we'll start equilibrium. We'll work on it next week as well. Your exam is in 2 weeks, minus a day, I guess. It will have solutions, kinetics, and as much equilibrium as we cover through next week. Your homework is due next Saturday, so February 13th. I'm making it due on Saturday because then I'll have the key available for you to look at on Sunday. So you can review your homework answers, make sure you're getting things right in preparation for the exam. So, yeah. Your exam is going to be, of course, open book, open note, whatever, open universe. It's a take-home exam, I guess you can say. You'll have 24 hours to do it, but please sleep at some point in there. And you're not able to use each other as resources. So, but that's that. So, with that, I guess we're done for today. We'll start chapter 15 tomorrow on chemical equilibrium. And yeah, we've survived kinetics. Hooray. So start working on your homework. Take a look at it. Only 24 problems this time. I'm very sorry. You'll see I've tried to pick ones that are not so blurry from the pictures I took. And I was just too lazy to retake the pictures. So if there's anything you can't see on any of those like data tables or numbers or something, let me know. I'll clarify for you what those are. But other than that, we're good. See you tomorrow then. Alrighty, take care.